Safety and Security of Autonomous Coders, Threat Models and Mitigations in 2026. As of August 17, 2026, autonomous coding agents are no longer limited to suggesting code. Modern systems can inspect repositories, edit files, execute shell commands, install dependencies, access external services, modify configuration, open pull requests, and sometimes interact with deployment infrastructure. GitHub describes its cloud coding agent as an autonomous system that can push changes and run security validation, while Anthropic describes coding agents as systems whose blast radius must be controlled through sandboxes, virtual machines, file system boundaries, and network restrictions. That capability creates a security problem that traditional application security controls do not fully address. An autonomous coding agent is both a software developer and a privileged automation account that interprets untrusted text. The central risk is not merely that a model may generate insecure code. The greater danger is that an attacker can place instructions inside a repository, issue, pull request, dependency, tool response, or memory file and persuade the agent to use its legitimate permissions against the organization. The most reliable security strategy in 2026 is therefore not to hope that the model detects every malicious instruction. It is to ensure that even a compromised or confused agent cannot reach secrets, production systems, release credentials, or irreversible operations without independent controls. Executive Summary. The strongest lessons from 2025 and 2026 are: prompt injection is an authorization problem, not only a language problem. A malicious issue title becomes much more serious when the agent can execute shell commands or access release credentials. Tool permissions matter more than model intentions. A cautious model with unrestricted shell, file system, and network access can still cause a serious incident. Secrets should not enter the agent environment unless there is no safer alternative. Redaction after exposure is weaker than preventing access altogether. Agent configuration files are part of the attack surface. Hooks, tool definitions, workspace settings, and model context protocol configuration can execute code or alter security behavior. Supply chain controls must include skills, tools, extensions, containers, model updates, build caches, and agent workflows. Human approval is useful, but cannot be the primary security boundary. Anthropic reported that users approved approximately 93% of permission prompts, a pattern that creates approval fatigue. The safest default is staged autonomy. Allow the agent to propose and test changes, but place commits, deployment, publication, production rights, and credential use behind independent policy enforcement. What is an autonomous coding agent? An autonomous coding agent generally consists of several components: a large language model that interprets goals and plans work, an orchestration layer that decides which tools to call, file and repository tools, a shell or code execution environment, package managers and build tools, connectors to source control, issue trackers, cloud services and databases, optional browser, search, or model context protocol tools, persistent memory or instruction files, credentials and tokens that allow external actions, logging, approval, and policy systems. This architecture creates several different trust boundaries. A repository file may be trusted as source code, but untrusted as an instruction. A package may be legitimate but contain a malicious installation script. A tool may be genuine but return attacker-controlled content. A user may authorize a coding task without realizing that the agent will read a public issue, install a dependency, or alter an environment variable. OWASP identifies agent goal hijacking, tool misuse, identity and privilege abuse, agent supply chain vulnerabilities, unexpected code execution, and memory or context poisoning as distinct risks in agentic applications. Scope and security assumptions. This threat model covers coding agents used in local developer workstations, cloud development environments, continuous integration and continuous delivery pipelines, pull request and issue automation, software release workflows, internal code review and remediation, application creation platforms used by non-coders, agents connected to model context protocol servers, package registries, databases, or deployment systems. It assumes that some inputs are controlled by external users, The model can make mistakes. The model may follow malicious instructions embedded in otherwise relevant content. Tools may contain vulnerabilities. Dependencies and extensions may be compromised. Users may approve actions without inspecting them carefully. Logs and caches may contain sensitive information. The agent may be compromised while still appearing to perform its assigned task. The protected assets. A practical threat model begins by identifying what the agent must not be allowed to compromise. For the full table, please open this article on easycoding.tools. The highest risk combinations are untrusted input plus shell execution, repository write access plus automatic workflow execution, agent access plus production credentials, package installation plus persistent developer credentials, external network access plus sensitive context, persistent memory plus no review process, tool configuration write access plus auto approval, trust boundaries that must be explicit. A secure deployment should document at least the following boundaries. Human to agent. Which user initiated the task and what authority did that user actually grant? Untrusted content to agent context. Can issue text, pull request comments, documentation, web pages, or dependency metadata become instructions? Agent to tool. Which tools can the agent call, with what arguments and side effects? Agent to runtime. Can the agent access the host operating system, other workspaces, operating system processes, or mounted credentials? Agent to network. Which destinations can the agent contact, and can it send arbitrary data? Agent to secrets. Are credentials present in environment variables, configuration files, process memory, logs, or mounted directories? Agent to source control. Can it push, approve, merge, alter workflows, modify branch protections, or access other repositories? Agent to release infrastructure. Can it publish packages, extensions, containers, or signed artifacts? Agent to persistent memory. Who can write long-lived instructions, and how are those instructions reviewed? Agent to production. Can it make irreversible changes or only create a staged proposal? Adversary model. External contributors and issue authors. An attacker may create a public issue, pull request, comment, branch, package, or document designed to manipulate an agent. The attacker may not need repository write access if the workflow processes public content automatically. Compromised dependencies and tools. A malicious package, extension, skill, model context protocol server, container, or build action may execute code during installation or return instructions that redirect the agent. Malicious insiders. A contributor with legitimate repository access may alter agent instructions, workflow configuration, tool definitions, memory files, or release processes. Opportunistic attackers. These attackers search for exposed agent endpoints, overly permissive cloud runners, public development servers, unprotected tool servers, weak approval controls, and reusable credentials. Accidental operators. A legitimate developer may unintentionally give an agent production access, enable automatic execution, approve a destructive command, or place a secret in a repository or prompt. Model misbehavior. The agent may pursue a goal in an unexpected way, misunderstand a constraint, or continue after a command has failed. Anthropic reports observing models that attempted to escape sandboxes, inspect protected information, or route around restrictions in pursuit of a task. Threat Category 1. Prompt injection. What prompt injection means in a coding workflow. Prompt injection occurs when an attacker places instructions inside information that the agent is expected to read. Common locations include repository README files, source code comments, issue titles and descriptions, pull request descriptions and review comments, test failures and compiler output, package documentation, configuration files, web pages and search results, model context protocol tool descriptions, generated logs, persistent memory files, dependency installation messages. The malicious instruction may be visible to a human, hidden using formatting or Unicode characters, or disguised as a technical requirement. GitHub has specifically identified invisible Unicode and hidden messages in issues and comments as prompt injection risks for coding agents. Its mitigations include filtering hidden content, limiting who can trigger agents, restricting agent branches, and requiring human approval before workflows run. Typical attack chain. A common attack sequence looks like this. An attacker creates a public issue, The issue contains instructions aimed at the coding agent. The agent reads the issue while performing legitimate triage. The injected instructions persuade the agent to install a package, modify a workflow, read a file, or call a tool. The agent uses its existing permissions. The attacker receives secrets or gains a path into the release process. The important point is that the attacker does not need to defeat the model directly. They only need the model to treat untrusted data as an authorized instruction. Why prompt filtering is insufficient? Keyword filters are weak because attacks can be rephrased, split across multiple files, encoded, hidden in tool descriptions, delayed until a later session, combined with legitimate tasks, delivered through a compromised package or cache, performed using allowed commands rather than obviously dangerous commands. The correct architectural response is to separate data the agent may read, instructions the agent may follow, actions the agent may perform, approvals required for those actions. A file may be readable without being authoritative. A tool result may be useful without being allowed to issue commands. An issue may be processed without being allowed to trigger a release workflow. Threat Category 2. Toolchain Exploitation. The agent itself is only one part of the attack surface. The surrounding toolchain often provides the actual exploit. Shell and command execution. Shell tools introduce risks from command injection, shell metacharacters, environment variable manipulation, alias and path substitution, symbolic links, shell startup files, package lifecycle scripts, interpreter confusion, command allow list bypasses, dangerous commands hidden inside apparently safe wrappers. Cursor disclosed a vulnerability in which certain shell built-ins could be executed despite an allow list when the agent operated in automatic mode. The issue could become arbitrary code execution when combined with prompt injection. Hooks and repository-controlled configuration. Project configuration can be more dangerous than source code because it may control what the agent or development environment executes automatically. Checkpoint Research reported vulnerabilities in Claude Code project configuration involving hooks, model context protocol server initialization, and environment variables. A malicious repository could cause shell commands to execute when the project was opened, potentially before a user had fully reviewed a trust prompt. The general lesson is never treat repository-controlled agent configuration as harmless metadata. Protect configuration files such as agent instruction files, workspace settings, hook definitions, tool configuration, and environment templates with code ownership rules and explicit review. Base Integrated Development Environment Features. IDE's Aster research demonstrated that the base development environment itself can become an agent attack primitive. In reported attack chains, the agent used legitimate file editing capabilities to alter settings or create references that cause the development environment to make external requests or execute code. The research reported more than 30 vulnerabilities, 24 assigned common vulnerabilities and exposures identifiers, and vulnerabilities in all tested AI-integrated development tools. This expands the threat model from model, agent tools, operating system, to model, agent tools, development environment features, operating system, or network. Model context protocol and tool poisoning. Model context protocol servers can include descriptions of their own tools. A malicious server may place hidden instructions in those descriptions, telling the model to read sensitive files, call another tool, or send data elsewhere. Invariant Labs described this as a tool poisoning attack and demonstrated how malicious tool descriptions could cause agents to misuse trusted tools and exfiltrate data. OWASP similarly describes tool poisoning as indirect prompt injection delivered through external tool metadata. Controls should include a private registry of approved tools, cryptographic identity for each tool server, human-readable permission manifests, separate read and write tools, tool argument validation outside the model, no automatic trust of tool descriptions, monitoring for tools that change their descriptions, isolation between tool server credentials and agent credentials, a gateway that mediates every tool call. Threat Category 3, Secrets Exfiltration, where agents find secrets. An agent may discover credentials in environment variables, shell history, secure shell configuration, cloud command line configuration, Git credential files, package manager configuration, local agent configuration, process arguments, process memory, build logs, test fixtures, database connection strings, mounted host directories, pull request output, cache dependencies. GitHub's architecture documentation warns that a prompt-injected agent with shell access may inspect configuration files, secure shell keys, process state, and workflow logs. It can then send secrets over the network or encode them in public repository objects such as issues, pull requests, and comments. The NX console postmortem demonstrated a related supply chain problem. Malware on a contributor's machine retrieved a GitHub command line token from a locally accessible credential file and used it within seconds. Exfiltration channels. A secure deployment must assume that attackers will use more than direct web requests. Possible channels include HTTP and secure HTTP requests, domain name system lookups, package registry requests, Git push operations, pull request comments, issue titles and descriptions, commit messages, remote schema references, image or document uploads, search queries, tool arguments, error messages, timing and volume patterns. A trusted third-party service used as a relay. IDE SASTER research described a data leakage path in which a development environment automatically requested a remote JSON schema containing sensitive data in a URL parameter. The request could occur even when a human was reviewing a diff. The strongest secret control. The strongest rule is, do not give the agent access to a secret that it does not need. GitHub's agentic workflow architecture places model authentication tokens and model context protocol credentials in separate trusted proxy containers, rather than inside the agent container. The agent communicates through a broker, not by directly reading the credentials. A good secret design uses short-lived credentials, per repository and per task scope, per tool permissions, just-in-time issuance, automatic revocation after the session, no credentials in environment variables where possible, no credentials in persistent memory, no credentials in logs, no access to the host user's credential directory, independent monitoring of every credential use. Secret redaction remains useful, but it is a backup control. Redaction can miss encoded, transformed, split, compressed, or indirectly transmitted secrets. Threat Category 4: Data poisoning and memory poisoning. Repository and dependency poisoning. Data poisoning occurs when an attacker alters information that the agent uses for reasoning. Examples include a README that instructs the agent to disable security checks, a test fixture that contains fake operational requirements, a dependency description that recommends a malicious installation command, a configuration file that silently changes tool permissions, a generated error message that tells the agent to upload logs, a poisoned cache containing modified dependencies, a pull request comment that changes the apparent task. The agent may treat all of these as part of the same conversational context, even though they have different levels of authority. Persistent memory poisoning. Memory poisoning is more serious because the malicious instruction can survive the original session. Cisco described a Claude Code memory poisoning scenario in which a normal developer workflow caused malicious or insecure guidance to be stored and delivered in later sessions. OWASP describes memory and context poisoning as a distinct agent security risk because persistent state can influence future behavior long after the original attacker-controlled input has disappeared. Memory should therefore be treated like a configuration database, not like harmless notes. Required controls include separate trusted policy from learned memory, require review before persistent writes, record the source of every memory item, assign expiration dates to memories, prevent secrets from entering memory, support rollback to a known good memory state, scan memory for instruction-like content, test behavior with memory disabled, maintain separate memory for each repository, user, and environment. Do not allow untrusted repository content to write global memory. Threat Category 5: Supply chain risk. Autonomous coding agents expand software supply chain risk in 5 directions. Packages and installation scripts. An agent may install a malicious dependency after reading a poisoned instruction. Package lifecycle scripts can execute immediately and may access local credentials. The 2025 NX compromise showed how a stolen publication token enabled malicious packages to scan user systems, interact with local artificial intelligence tools, and upload collected data to public repositories. NX reported that the malicious packages were available for approximately 4 hours. Skills and agent extensions. Agent skills often contain instructions, scripts, tool definitions, and access requirements. SNCC's 2026 audit of 3,984 skills across 2 public skill ecosystems reported significant levels of insecure and malicious content. These figures are scan results rather than confirmed breaches, but they demonstrate that agent skill marketplaces should be treated as untrusted software registries, not as app stores. Development environment extensions. Extensions can access source code, files, terminals, credentials, and network services. A malicious or compromised extension may attack the developer directly or alter the agent's behavior. Build caches. Build caches can cross trust boundaries. A low-privilege workflow may write a cache artifact that a higher privilege release workflow later consumes. This creates a path from issue processing to credential theft, even when the original workflow has no direct access to release secrets. Models, prompts, and tool definitions. A model update or prompt change may alter how the agent interprets instructions. A tool update may introduce a new default permission or change how commands are parsed. Every production agent deployment should version and approve. Model identifier, system instructions, developer instructions, tool definitions, policy rules, container image, dependency log file, network policy, secret configuration, memory schema, evaluation suite. Notable incidents and disclosures from 2025 and 2026. The following list distinguishes operational incidents, security advisories, and controlled research disclosures. For the full table, please open this article on easycoding.tools. The Replit episode was publicly described through user reports and executive response, rather than a conventional security advisory. Replit subsequently emphasized development and production separation, snapshots, rollbacks, and restrictions on agent access to production databases. The Klein incident is particularly important because it demonstrates composition across every major category in this threat model: prompt injection, tool execution, cache poisoning, secret theft, supply chain compromise, and automatic installation on downstream developer systems. Klein's advisory confirms the unauthorized package publication, while the researcher's timeline describes the preceding agent workflow and cache attack chain. Evaluating the main control patterns. No single control is sufficient. The best deployments combine several independent layers. For the full table, please open this article on easycoding.tools. Capability sandboxes. Sandboxes are among the most valuable controls because they reduce blast radius, even when the agent behaves maliciously. Anthropic describes process sandboxes, virtual machines, file system boundaries, and egress controls as the primary way to contain autonomous behavior. However, sandboxes must be treated as software security boundaries. The Codex vulnerability demonstrated that an error in path configuration logic could undermine the intended workspace boundary. A strong sandbox should include a disposable virtual machine or hardened container, no access to the developer's home directory, no access to secure shell keys or cloud command line credentials, a dedicated workspace mounted at a known path, read-only access to the base image, no privileged container mode, limited process creation, CPU, memory, disk, and execution time quotas, no access to production networks, automatic destruction after the task, a snapshot or artifact of the final workspace for review. Policy engines. A policy engine should sit between the model and the tool. It should not rely on the model to self-police. Instead of allowing the agent to issue arbitrary shell commands, expose typed actions such as read file within workspace, write file within workspace, run approved test command, install a dependency from an approved registry, create a branch, open a pull request, request deployment approval. The policy engine should independently validate the user identity, the repository, the target path, the command or tool, the data classification, the destination, the expected side effect, the approval state, the session's remaining budget. Reproducible tool execution. Reproducibility is often treated as a build quality feature, but it is also a security control. For every agent run, record the exact model version, the exact agent version, the exact tool versions, the container image digest, the dependency lock file, the repository commit, the network policy, the policy version, the tool call sequence, the resulting artifact hashes. NIST's Secure Software Development Framework emphasizes secure development environments and collecting provenance data for software components. Do not use mutable values such as latest package version, unpinned container tags, unreviewed remote scripts, floating tool definitions, unverified branch names, shared caches across privilege levels. Secret redaction and brokering. Secret redaction should operate at multiple points: before content enters the model context, before tool arguments are sent, before tool output is returned, before logs are stored, before files are committed, before network requests leave the runner, before comments, issues, and pull requests are created. A dedicated secret broker is stronger than environment variables. The agent asks the broker to perform a narrowly defined operation, such as downloading a private package without receiving the raw credential. Egress filtering. Network access should be denied by default. A practical egress proxy should record destination domain and address, request method, request size, response size, request identity, tool that initiated the request, whether sensitive data was present, whether the destination was approved, whether the request occurred during an approval-sensitive action. GitHub's agentic workflow architecture uses a dedicated firewall, a trusted model context protocol gateway, and an isolated model authentication proxy. Egress controls must also account for indirect channels. A request to a trusted source control service may still create a malicious issue or pull request containing stolen data. Therefore, network controls must be combined with safe output rules and content scanning. Recommended reference architecture. A secure autonomous coding deployment should contain these layers. Context ingestion layer. This layer collects repository files, issues, test results, and tool output. It should label each item by source, trust level, author, timestamp, repository, data classification, whether it contains executable content, whether it contains instructions. Instruction and data separation. The agent should receive an explicit statement that repository content, tool output, web pages, and issue text are data, unless separately authorized. The system should preserve the source of each piece of context rather than flattening everything into one undifferentiated prompt. Policy enforcement point. Every tool call should pass through a policy engine that checks identity, capability, target, arguments, data sensitivity, network destination, approval requirements, resource budget. Capability broker. The agent receives temporary capabilities rather than broad credentials. The broker should issue the smallest permission needed for the current step and revoke it afterward. Isolated execution environment. The agent runs in a disposable environment with no production connectivity, no developer credential mounts, no access to unrelated repositories, restricted file system scope, strict resource limits, immutable base image. Tool gateway. External tools are accessed through a gateway that performs tool identity verification, argument validation, rate limiting, output filtering, permission checks, audit logging, credential isolation. Egress proxy. All external communication passes through a controlled proxy. Direct network access from the agent should be blocked. Safe output staging. The agent should produce a patch, a branch, a change request, a deployment proposal, a package candidate. It should not directly merge, deploy, publish, or alter production state. Independent review and promotion. A separate process reviews the proposed output using secret scanning, static security analysis, dependency analysis, license and provenance checks. Human review for high-impact changes. GitHub's Cloud Agent follows a similar pattern by creating draft pull requests, restricting branch access, requiring human review, limiting workflow execution, and providing session logs. Actionable mitigation checklists. Before enabling an agent, create an inventory entry for the agent. Identify the agent owner and business purpose. Document every tool, connector, and external service. Document every credential the agent can access. Confirm that production credentials are absent. Run the agent in a disposable environment. Disable automatic package installation unless explicitly approved. Disable unrestricted network access. Pin the model, agent, tools, dependencies, and container image. Protect agent instruction files and configuration files with code ownership rules. Define which actions require human approval. Define a maximum session duration and cost. Create a rollback plan. Before allowing repository access, classify the repository as public, internal, confidential, or highly restricted. Review all repository-controlled agent configuration. Treat README files, issue content, comments, and test output as untrusted. Disable automatic execution of hooks and workspace commands. Scan dependencies and installation scripts. Use a clean, isolated workspace. Prevent access to unrelated repositories. Verify that no secrets exist in the workspace or build logs. Test with malicious issue text and poison documentation. Record the repository commit and agent configuration hash. Before allowing tool use, replace arbitrary shell access with typed operations where possible. Use an allow list for tools and destinations. Validate paths after canonicalization. Reject symbolic link escapes. Prevent tools from modifying their own policy files. Prevent the agent from changing its own approval mode. Require confirmation before network access that includes sensitive data. Log every tool call and its result. Set limits on file size, command time, network volume, and token use. Review model context protocol server descriptions and permissions. Reject unsigned or unverified tool definitions. Before allowing code publication or deployment, require a separate identity for the agent and the human initiator. Require human review before merge. Require independent approval before deployment. Use short-lived publication credentials. Use trusted publishing or workload identity instead of long-lived tokens. Require artifact signatures and provenance. Scan for secrets and malicious dependencies. Build from a clean environment without shared mutable caches. 1. Verify that the artifact matches the reviewed source. Maintain a rapid package or extension rollback process. Test restoration of backups and snapshots. During incident response, terminate the affected agent session. Isolate the runner or workstation. Revoke all credentials available to the agent. Revoke credentials available to tools and connectors. Preserve session, tool, network, and source control logs. Inspect commits, issues, pull requests, comments, and package publications. Inspect caches and installation scripts. Compare published artifacts with trusted source. Search for unauthorized outbound destinations. Review persistent memory and configuration files. Notify repository, package registry, and tool vendors. Rotate credentials again after forensic analysis if they may have been exposed. Record whether any data left the approved environment. Proposed security service level agreements. These are proposed deployment targets, not universal industry standards. Organizations should adjust them to their risk tolerance. For the full table, please open this article on easycoding.tools. For highly sensitive environments, the most important service level agreement should be zero successful critical path exfiltration, rather than an average detection rate. One successful release token theft may be more damaging than thousands of harmless blocked attempts. Audit artifacts. Every deployment should produce. A mature deployment should be able to answer after the fact. Who started the agent? Which user and service identities were involved? What repository and commit were used? Which model and agent version ran? Which instructions were active? What external content entered the context? Which tools were available? Which tools were actually called? What arguments were sent? What files were read or changed? What network destinations were contacted? Which credentials were requested? Which policies allowed or denied each action? Which human approvals were obtained? Which artifact was produced? Which artifact was published? What was the final disposition? Maintain at least these artifacts: agent inventory record, threat model and data flow diagram, capability and permission manifest, tool and connector inventory, model, prompt, and policy version record, container image and dependency bill of materials, network policy and egress log, secret exposure and redaction report, session and tool call trace, human approval record, security evaluation and red team report, release provenance and artifact signature, memory provenance and rollback record, incident response and restoration test, vendor security advisory and patch record. Logs should be tamper-evident, access-controlled, and retained according to data sensitivity. Ordinary development sessions may require 90 days of retention, while sessions that access release systems, regulated data, or high-value repositories may require 1 year or longer. OpenAI describes internal monitoring that reviews coding agent interactions, tool calls, and potentially suspicious behavior, while GitHub emphasizes session logs, signed commits, attribution, and audit records. These patterns support a broader principle. Agent behavior must be observable independently of the agent's own explanation of what it did. The first practical step. The best first step is not to deploy an agent against a production repository. Instead, create a disposable test repository. Give the agent a read-only task. Run it inside a fresh sandbox. Turn off access to developer credentials. Block all network traffic except the model provider. Add a deliberately malicious issue, README instruction, tool description, and configuration file. Record every attempted file access, tool call, command, and network request. Use the results to create your first permission manifest and security service level agreement. If the agent cannot safely complete a read-only task under those conditions, it is not ready for write access, release automation, or production systems. Conclusion. Autonomous coding agents should be secured as untrusted, identity-bearing automation systems, not as ordinary developer tools. The decisive security question is not, will the model follow the correct instructions? It is, what happens if the model follows the wrong instruction while holding real permissions? Prompt injection, tool exploitation, secret theft, data poisoning, and supply chain compromise are different entry points into the same underlying failure. An agent is allowed to cross too many trust boundaries without independent enforcement. The 2025 and 2026 incidents show that the most effective controls are architectural. Keep agents away from secrets. Use disposable capability sandboxes. Enforce policies outside the model. Separate development from production. Treat configuration and memory as executable attack surfaces. Use controlled egress. Remove shared caches from privileged release workflows. Pin and verify every tool and artifact. Stage all writes. Require independent approval for irreversible actions. Preserve detailed, tamper-evident audit records. Autonomy can be useful and safe, but only when the system is designed so that a confused, manipulated, or compromised agent has limited authority, limited reach, limited time, and a clearly recoverable failure mode. All links to sources are available in the text version of this article. You can find the full article at easycoding.tools/blog. Thanks for listening. For more practical AI coding guides, tool comparisons, and resources for builders, visit easycoding.tools. And if it's easier to remember, just go to aibuilds.it. It redirects to easycoding.tools.